subarray, it's probably going to be n squared. But actually, that's not quite true because we only care about the subarrays that are divisible by k. So let me show you what that would actually look like. Let's just say we have some random subarray. And let's say that our k value is equal to 3. So we only care about subarrays that have a length that is divisible by 3. And for some reason, like maybe I'm just not familiar with the term subarray, but I always thought a subarray could technically be empty. Like technically an empty subarray is a valid subarray, but I guess in this problem that's not the case. We only care about non-empty subarrays. So that's a little bit different for me. I don't know, maybe I'm just forgetting though, but anyways. So we can't consider an empty subarray. Like that would mean that that sum of that subarray is equal to 0. But as you can see in this example, 0 is not the result. -10 is the result because we have to pick a non-empty subarray. And I think the one with the smallest sum is this one with a length divisible by 4. So in this example, let's say we're starting at the beginning. We want all subarrays starting at this element. There's not as many choices as you think. There's this one because it's of size k, size 3. And there's also this one. And if we try to get one of size 9, it doesn't really exist. We don't have enough elements for that. So there's only 2 subarrays that we need to check. And so far, this doesn't seem more efficient than n squared. So we have that. And then starting from here, this element, we could do something similar. These 3 elements, this subarray, and then can't really go further than that. And we could keep doing that, right? So from this guy, same thing. And I won't draw everything out. But obviously, the main bottleneck with this approach is that, like, to get the sum, we have to get all these elements. And then to get this sum, we have to add these elements as well. But there's an easier way. Do you know a way where we could just pick any arbitrary subarray, like this one, or anything, right? Maybe this one of size 3. Could we just get that sum in constant time? I know of one such technique. It's called the prefix sum technique. So if we computed every single prefix sum, which would mean like the value here is going to be the sum of everything here. The value here would be the sum of everything here. And if we had that, then if we wanted just the sum of this, we could take this prefix sum, subtract from it this prefix sum. So I'm not going to cover like prefix sums super in depth. I'll show you the code for them, but basically I'll show you like what the prefix sum of this array would be. It's pretty simple to calculate. You just keep a running sum as you iterate from left to right, and then just keep appending that to the array. So the first prefix sum is going to be 1. This prefix sum is going to be 2 plus the previous value, 1, which is 1. Then this plus that, which is 6. This plus that, which is 10. And then you just keep going like that. So if we wanted the sum of this, we would take 21, which gives us everything. We would subtract from it 6, which gives us that. So then we'd be left with 15. Okay, so why is that better? Because yes, for each starting position, we're going to have to look at like multiple subarrays, but how many subarrays at most could we have starting at any given element? Well, given that we're not, just adding one element each time, we're going through multiples of k, we're going to consider every single starting point. So that's going to be big O of n, but then the next term that we have is actually going to be n divided by k, because that tells us how many different subarrays we could actually have starting from that element, because we're incrementing by k each time. Like the length of that subarray is growing by k each time. So we're not incrementing by 1. If we had 1 in this denominator, yes, it would just turn into n squared, but we don't have 1, so it turns into this. The reason I'm even talking about this solution is because I'd rather do this than just jump into the optimal solution, because I think if you were not able to come up with the optimal solution, that this solution is actually much more approachable. And not only that, but this solution actually will bring you a lot closer to the optimal solution, which is going to be of time big O of n. So let me actually show you the code for this approach. So this is the code. You can see it does get time limit exceeded, and this was my code for it. It's not super, like there's nothing fancy going on. It's just building the prefix sums and then initializing the result to a really negative value because we're trying to maximize that. And then we have 2 nested loops. One is going to determine the start value, and then the inner loop j is going to be incremented by k each time, just trying to maximize the result. There's an edge case where the prefix sum might be out of bounds. In that case, we would just set it to 0. But now we're gonna get into the more optimal solution. And the idea behind the optimal solution isn't, in my opinion, too different from this solution. So I'll try to walk you through my logic. So rather than thinking about it in terms of like, what is the maximum sum subarray we could get that's valid, right? That's a length multiple of this. That's starting from this position, right? When we do that, we kind of do this, and then we do this, and we just kind of keep going like that. But what if we invert our thinking, which is a common technique when you're trying to solve DSA problems? You have to kind of think about the problem in reverse. So let's try something else. Rather than doing that, let's try to think of it in terms of, what if we were trying to get the subarray ending at this position, the best one that's a multiple of k ending at this position? Well, let's start from the beginning, because it's actually really easy when you do that, at least from here. So what's the best one that we could get from here? Well, the size so far, the length, is 1. So that's not even a multiple of k yet. So let's keep going. And actually, in our case, k is 3. So still, let's keep going. We're here now. Well, still not a multiple of k. Okay, now we're here. The sum is 6. And by the way, in this example, it makes it pretty obvious that since everything is positive, we would probably just want to take as many elements as we can. But I'll try to change up the example as we go and introduce some negative numbers as well. But now we're finally at the case where this is of length 3. So what's the best subarray that we could pick here that's non-empty? Well, there's no elements that come before it. So this is really the only one. This is the only choice that we have. And the sum is 6 so far. Okay, so that's one valid subarray. Now, what's the best one ending here? So we have these 4 elements. Well, the length of this is now equal to 4. Kind of a problem, because you take that length, you mod it by k is 3, you're going to get 1 as the remainder. So it's not divisible by k. But the good news is that this 1 tells us that if we were to remove a prefix from this array of size 1, well, then our length would be valid. So we just pick the prefix that has a length of 1 and remove it, and now this is valid. The length is valid at least. So the best one that we could create from ending at this position is going to be this one. So we take the entire sum subtracted by that prefix. And it's going to kind of keep going like this for now, but you're going to see something interesting is going to happen in a second. You might have already noticed what that's going to be, or maybe you haven't yet. But if you haven't, then just keep going through the example, see what you discover. So now we're here. So far we have this. The length is 5. You mod that by k, you're going to get 2. So we can do the same thing. Just remove a prefix of 2. We have to do that to make this valid. That's the only way to make this valid. So then we get this sum. And I'm not really keeping track of our sum, but remember, we're just going to keep maximizing it, whatever it ends up being. Okay, so we have that so far. Now we're going to keep going. This is where it gets kind of interesting. So now we're here. The length of this is 6. You mod it by 3, you get 0. So we find that this is divisible by k. So this is a valid subarray. And so in this case, since everything is positive, yes, this is the maximum subarray. But it didn't have to be that way, because what we're trying to ask is, what's the maximum valid subarray ending at this position? There is one other valid subarray ending at this position, and that would be the one that removes a prefix of size 3. Or, and this is the key observation that you could make, it's not that that prefix has a size of 3, it's that that prefix that we're trying to remove has the same remainder as this one. The length of that prefix, when you take the remainder, it's the same as the remainder that we just computed. So that's the key observation, that we want to remove only prefixes that have the same remainder as the current one that we just found, because that will make the length valid. That will get rid of like the extra offset that we have and make it valid, even if it's already valid. So if there's multiple choices, and in this case, there are multiple choices. The two choices are, we either remove the empty prefix, we don't remove anything, which would be to say remove 0, or remove this prefix that has a sum of 6. So which one of these would we rather remove? We want to take the minimum of all the prefixes that we can possibly remove and only remove the minimum one, because that's what's going to maximize the subarray ending at this position. And in this case, like I said, since everything is positive, we wouldn't want to remove anything. We remove and only remove the minimum one. Valid. That will get rid of like the extra offset that we have and make it valid, even if it's already valid. So if there's multiple choices, and in this case, there are multiple choices. The two choices are we either remove the empty prefix, we don't remove anything, which would be to say remove 0, or remove this prefix that has a sum of 6. So which one of these would we rather remove? We want to take the minimum of all the prefixes that we can possibly remove and only remove the minimum one, because that's what's going to maximize the subarray ending at this position. And in this case, like I said, since everything is positive, we wouldn't want to remove anything because we have that choice. We don't have to remove anything, at least in this particular case. But obviously, if I made these elements negative, then we would want to remove that prefix. Even if I just made this element negative, we would say, okay, our choices are to remove the empty prefix 0 or this prefix. Actually, this one also turns into 0, so maybe I add the negative there. So now it becomes -2. So which prefix would I rather remove, the 0 or the -2? Probably the -2, because that's going to make this more positive. Now I'm going to keep going with this, but there's one thing I haven't covered yet. So now it becomes this element negative. We would say, okay, our choices are to remove the empty prefix 0 or this prefix. Actually, this one also turns into 0, so maybe I add the negative there. So now it becomes -2. So which prefix would I rather remove, the 0 or the -2? Probably the -2, because that's going to make this more positive. Now I'm going to keep going with this, but there's one thing I haven't covered yet, and maybe you'll be able to figure it out by yourself. If we're still going to have to iterate over every single possible prefix, it's not going to be any more efficient than the other solution I showed you, because we're going to have to possibly iterate like k different times for every prefix. Or I think something like n divided by k times. So it's going to end up being the same as before. So there is a technique we're going to do to mitigate against that. It's going to involve a data structure that you're pretty familiar with. And it's going to involve, rather than computing the minimum on the fly, how about we just store the minimum? So this is a pretty big hint. And the last hint would be store the minimum corresponding to that remainder. But anyways, so last case would be here. What's the max subarray ending at this position? Well, right now the length is 7. You mod that by 3. You get 1. You remove a prefix that has a remainder of 1. Which choices do we have? We have this choice or we have this choice. Again, we take the minimum of these. This one has a sum of 1. This one has a bigger sum, I think 10. So we remove the smaller one. Okay, so now I'm actually going to jump into the solution and I'm going to spoil the algorithm for you, which is that rather than computing that minimum on the fly, we're going to use either a hash map or an array to store that. And the reason we can use an array as well is because what I'm going to do is I'm going to map the remainder of like any given subarray, and I'm going to map that to the minimum sum. So just to make this clear, look, this subarray and this subarray, they have the same remainder. And even this subarray as well. They all have the same remainder. So which one of them has the smallest sum? Well, since these are all positive, this one has the smallest sum. So that's the one we would store. We would say, okay, for the one that has a remainder of 1, the length has a remainder of 1, that is, the minimum sum is going to be 1. But at the same time, recognize that when we get to here, we don't want to remove this subarray, like the entire one. We can't remove more elements than we actually have. So actually this data structure that we're going to build, and I'm going to choose an array, we're not going to build it up front. We're going to build it as we go. So let's go ahead and do that. So I'm going to have my little data structure down here. It's going to be of size k. How do I know it's going to be of size k? Because the remainder is going to be anywhere from 0 to 2. It's going to be 0, 1, or 2. It can't be 3, and it can't be bigger than 3 because that's how we're computing the remainder. So once you know that, it becomes doable. So we have 0, 1, 2. Remember, these are the remainders. Initially, what we can say is that these are all going to be some big number. So you could say like infinity or whatever big integer that you have in your language of choice. So these are all going to be some big number, but we are actually going to initialize this one to 0. You don't have to do it that way. You could add like an extra if statement, like on the case where the length is exactly equal to k, and then you could handle that slightly differently. But it's easier if you just initialize this to 0, and the reason for that is because when we're here, we want to be able to say that we can remove the empty prefix that is technically allowed, the prefix with a remainder of 0. So we want to say that that has a sum of 0, just to make the math work out. So then why am I putting infinity in these other positions? Well, again, to make the math work out, because on like this subarray, when it's of size 2, we're going to say, okay, well, the remainder of this is 2, so we can remove a prefix from this of this sum. And the reason we put this infinity is because then that sum ends up being negative infinity, and that basically tells us it's invalid, because this array is clearly invalid. It's not even as big as 3. So again, it just helps make the math work out, but you don't have to handle it this way. You can add some extra if statements if that is more understandable for you, but this just makes the code a little bit cleaner. So I'm going to go through this case, and then we're going to get the remainder as 1. We're going to get this. We're going to say, okay, we can take the total sum that we have so far, which is 1, subtract from it infinity. That's going to give us negative infinity. We're going to do the same thing in this case. Then we're going to finally get to this case where we're going to have a total sum of 6 so far. We're going to subtract from that. Well, first we're going to find the remainder. 3 modded by 3, that's 0. So then we map to this sum. That's the smallest sum that we've seen with a remainder of 0. That just means it's an empty subarray. We remove that, then we get 6. So that's our sum so far. Oh yeah, and I guess I didn't mention that as we're actually going, we're going to be updating this. So when we were here, while we would have subtracted negative infinity from this, after we were done with that, we would have taken the length of this and said it's 1. And of course, when you mod that by k, you also get 1. And then we would say, okay, well, the smallest sum we've seen now with a remainder of 1 is 1. So we can update this to be 1. And we could have also done the same thing over here. We can update this to be 2. When we're here, we compute the sum to be 6. So we don't put that over there because it's not smaller. We always want the smallest sum to be here. So we don't do that, and then we just continue. Now we are here. Total sum is 10. The remainder of this length is going to be 1. So we have to remove this subarray to make this one valid. And this is the smallest sum that we could remove. So we get 10 minus 1, which is going to be 9. And we're not going to replace this value with the sum that we have right now because it's bigger. So the rest of this example, I think, is going to be pretty straightforward because all of these are positive. But if you want to change it up, you can introduce some negatives here and see if the solution also works on that. But just to kind of quickly go through the rest of this, we're going to get this sum, and then we're going to remove this prefix, which to here. This one is definite. Some other problems like this one, like I mentioned, those two problems at the beginning of the problem are almost identical to this one. So I'm going to initialize